All right, so we're at the end of differential equations, and so I thought for an overview, this video is going to overview linear differential equations, and that's because the overall theory of the linear differential equation is going to be the same, whether it's first order, second order, or a system of differential equations. Okay, and so what is the theory for the linear differential equation? Well, first of all, the operator or a differential equation is linear if the operator is linear, meaning that's the operator on y, I should say, when it's like a first or second order. Okay, so if we have something like, well, we know what a linear differential equation is. It's y prime plus p of t times y equals g of t, or a second order, or a system. Okay, now this is actually an autonomous system. So to get the non-autonomous part, we could add on functions of t, but we didn't talk about that, so I won't do that in this. Okay, but anyway, see if I can talk today. These three are all linear systems, right? And so what does that imply? That implies that we solve them by splitting the solution apart into autonomous, or sorry, not autonomous, but homogeneous. The homogeneous part, y sub h, is the homogeneous part. So it's the part where g of t is equal to 0, and that's actually what we're talking about here. So this is the homogeneous system of equations here. And then y sub p will be the particular part. Okay, and then we get the full solution by adding these pieces together. And so that's how we get the full solution. Now there's something similar to this just for the y sub h, right? Because we know that if y1, y2, and so on down to yk are solutions to the dE, so is any linear combination of y1 through yk. Do you remember what that's called? That's the principle superposition. Yeah, so that's the superposition principle. And so that has to do with this piece, right? And so that is our goal initially, is to get the homogeneous part of the solution first, and then the second part is to get the particular part. Okay, so to get the homogeneous part, now there's a couple of ways of doing it here. So with y prime plus p of t times y equals 0, we actually don't need to break this one up because the integrating factor actually gives us everything. But if we wanted to, we could set that equal to 0 and solve for the homogeneous part, because this is now also a separable differential equation, and so you could write this as 1 over y dy is equal to p of t dt. And so the natural log of y equals the integral of p of t. And so then you'll see that the y is equal to, when I'm writing this, I could put this plus c here on the end, or it could be implied by this integral. Okay, so that's going to be, in any case, it would be a constant in the front. So I could say a e to the integral p of t dt. Okay, we've seen that expression before, because without the a here, right, that is actually the integrating factor. And so we see that this is also the homogeneous part of the solution for first order differential equations. We didn't talk about that before, but that's what it really is. And so with the other cases, now I should say, do we know how to get the y sub h if we're given the general second order differential equation? We do not. We don't have a general technique for y sub h, and that's when these are actual functions of t. However, there are special cases, and there's also we also know that if y1 is one solution to the homogeneous equation, we have several ways of getting y2. Do you remember what they are? One way is to compute the Wronskian two ways. Right, we've done that several times. But the other way is reduction of order. And that's where you assume that y sub 2 is some function, should we call it u, times y1, and then plug that into your differential equation and get the differential equation in u. Good. I wrote it this way because this is very suggestive, right? We had a variation of parameters which was very similar ansatz to that. Okay, but continuing along, since we don't have a general case, right, we focused on ay double prime plus by prime plus cy equals f of t. And our focus was on this because of the physics behind it, and that is the mass spring system. And so in physics you would study this quite a bit. And so we looked at all the special cases with the A, B, and C. I'll bring those up again in just a bit, but I just wanted to finish the overview first. Okay, so just to finish this off with the other, in the general case, so at this point, right, we know how to compute the homogeneous part of the solution. So let's compute the particular part. For y sub p, we had what techniques? Method of undetermined coefficients. Whoops. And then we had variation of parameters. Okay, method of undetermined coefficients is just where you go in and you guess that your function is of the same form as your forcing function. And variation of parameters is where we assume that y sub p is u1 times y1 plus u2 times y2, where y1 and y2 solve y sub h. So we assume that we have those, and then we can plug that into your general form, and you can find the solution to the particular solution. Good. Of course, that's a lot of work. You wouldn't want to do this if you could just do the method of undetermined coefficients instead. Okay. Now, finally, before I leave this section, what I wanted the last part of this is just hooking it up with the new material. Okay, so for the new material, our linear system, or our linear differential equations, is a system. And so for x prime equals ax plus by, and y prime equals cx plus dy, we start off with our ansatz like we did with our mass spring system, except the ansatz in this case, we'll just go ahead and write it down as x of t is equal to e to the lambda t times v, right? And when you plug it in, we find that a times v equals lambda times v, or a minus lambda v1 plus bv2 equals 0, cv1 plus d minus lambda v2 equals 0, and this is the system of equations you want to remember, because this is how you find, solving this system of equations is how you find the lambdas and the v's. Right, because what's special about this system of equations? We do not want v and v1 and v2 to have to be 0, right? We want non-zero solutions to this. The only way you get non-zero solutions to this is if the determinant, let me write it this way, a minus lambda b c d minus lambda is equal to 0. So if the determinant is equal to 0, that means these two equations are constant multiples of each other, and that gives you a way of getting your v's. So that's pretty tricky. And so through this extra equation here called the characteristic equation, we're able to solve for our lambdas. And in the case of a 2x2, you get this nice expression. But this is only true for the 2x2 system, right? Why do I say that? If you had 3 differential equations and 3 unknowns, then this is going to be a cubic polynomial instead of a quadratic. Or if you have n equations and n unknowns, this would then be a polynomial in degree n. So you would have a full degree n polynomial to solve. Okay, and then we went through in each case using the quadratic formula, and we said this is the form, and this is how you solve it. And so then we got our x sub h in that case. And so far in the systems, linear systems, we only know how to solve for the homogeneous part, but you can imagine that solving for the particular part, you could do something similar to method of undetermined coefficients. We're not going to do that for the exam, but it is possible to do that. Okay. And so for the linear system, we have our homogeneous part of the solution. Good. Of course, I should say that there are other ways of solving this system as well, right? Other ways. So one, you could convert to a second order system, or second order DE, and solve using chapter 3. By chapter 3, I mean we're back to solving the mass spring equation, right? And of course, there's also, if you write dy over dx is equal to, I lost my notation here. X prime is f of xy, y prime is g of xy. Then you could rewrite the linear system, or you could compute dy over dx as dy over dt. Maybe I'll just write that, divided by dx over dt. And so that would be g of xy divided by f of xy. And you could hope that this is a differential equation we could solve from chapter 2 of the book. Whoops, I just ended up off the page. Good. So I've got about 30 seconds before I'm automatically cut off. So I will stop it there. And that has been the overview of linear differential equations.